Picture this for a second. You have a ball of lightning floating in your living room. It's glowing, it's humming, and it's just sitting there. It's not exploding, it's not vanishing in a microsecond, it's stable. Now, according to standard physics, that shouldn't happen. A ball of plasma, hot ionized gas, should just blow itself apart instantly because of the pressure. But we have these reports going back centuries of ball lightning. And then we have this report, right? The Nachamkin report. It's a fascinating piece of Cold War era physics that tries to explain the impossible.
Exactly. Today, we are digging into a technical report from 1992 titled Force-Free Time-Harmonic Plasmoids by Jack Nachamkin. This was research done for the Air Force Phillips Laboratory. And Eloise, when I first looked at this, I thought, okay, force-free plasmoids, sounds like sci-fi technobabble. But the implications here are actually wild. We're talking about potentially stable, self-contained energy structures. So let's start with the basics. What exactly is a plasmoid, and why is this report so obsessed with making it force-free?
So a plasmoid is essentially a distinct structure made of plasma and magnetic fields. Think of it like a smoke ring, but instead of smoke, it's made of charged particles and magnetic energy. The problem, as you hinted at, is stability. Usually, if you bundle a bunch of charged particles together, they repel each other. They want to expand. They want to dissipate. The force-free part is the magic trick. Nachamkin is describing a mathematical state where the magnetic fields and the currents within the plasma are arranged in such a perfect way that the Lorentz forces, the forces that usually push and pull on the charged particles, cancel each other out.
Wait, so the force is zero? It's basically pulling on itself in all directions equally so it stays put?
That's a good way to visualize it. In a force-free field, the current flow is parallel to the magnetic field lines. Usually, current flows across magnetic lines, which creates a force. That's how electric motors work. But if they run parallel, the cross product is zero, no force. It's like the plasma is essentially surfing its own magnetic wave without wiping out. Nachamkin's specific contribution here is adding the time-harmonic element. He's not just talking about a static field, he's talking about an oscillating electromagnetic wave trapped inside this plasma ball.
Okay, so it's vibrating. It's a standing wave.
Precisely. It's a standing electromagnetic wave. And what's really cool about this report is that he connects this electromagnetic stability with fluid dynamics. He suggests that the plasma isn't just sitting there, it has a vortical motion. It's swirling. And that swirling motion creates a pressure that counteracts the electromagnetic pressure that would otherwise blow the thing apart.
So it's a hurricane of plasma, but the wind speed and the magnetic field are perfectly balanced to keep it locked in a sphere. That is incredibly elegant. But why were they researching this in 1992? I mean, was the Air Force trying to build ball lightning weapons?
Well, the report actually gives us a glimpse into the motivation in the preface. Nachamkin mentions that the research was spurred by experiments from the late 60s and early 70s regarding fusion weapons and laser fusion at Los Alamos. They were seeing anomalies. When they blasted pellets with lasers, they saw symmetries in the debris they couldn't explain, and they saw stability in small plasma volumes that shouldn't have been there.
Anomalies are always where the fun science hides.
Always. They were trying to understand inertial confinement, basically how to keep a fusion reaction sitting still long enough to get energy out of it. If you can create a stable plasmoid, a force-free little packet of energy, you might have a better way to sustain fusion. But Nachamkin also explicitly mentions ball lightning and charge clusters as phenomena that might be explained by this theory.
I want to drill down on the how of this. The report talks about a critical frequency. It seems like this is the make or break factor for these things existing. What is that about?
This is one of the key technical insights in the paper. Nachamkin shows that for a plasmoid of a certain size, there is a specific frequency threshold. Below this frequency, the plasmoid is unstable. The math shows that the current would have to be carried by the ions, the heavy nuclei, which is physically impossible at these speeds. But above this critical frequency, the current is carried by the electrons, and something weird happens to the energy state.
Weird how?
The system enters a local energy minimum. Essentially, if you tried to disturb the current, say a random fluctuation tried to nudge the electrons off their path, the system would resist. It acts like an elastic body. It wants to snap back to its shape. This self-correcting mechanism is crucial because a ball of plasma is usually chaotic. This theory suggests that if you pump it with a high enough frequency, it becomes rigid and self-repairing.
That is fascinating. It's almost like spinning a top. If it spins fast enough, it resists falling over. If the frequency is high enough, the plasmoid resists falling apart. But there's a catch, isn't there? The report talks about radiation.
if I have a ball of oscillating charge, shouldn't it be broadcasting radio waves like crazy? And wouldn't that make it lose energy and die?
You've hit on the exact problem with most plasmoid theories. Usually, yes, oscillating charges radiate energy. If they radiate, they cool down and the structure collapses. But Nachamkin proposes a solution based on resonance. He argues that if the plasmoid is exactly the right size, specifically if its radius corresponds to a 0 of a spherical Bessel function.
Whoa, slow down. Spherical Bessel function? Give me the non-math major version of that.
Okay, think of a drum head. When you hit it, there are certain spots on the drum that don't move up and down. Those are nodes. A spherical Bessel function is just the 3D mathematical description of those wave patterns in a sphere. Nachamkin says that if the plasmoid is the specific size where the electric and magnetic fields are effectively 0 or tangent at the surface, it doesn't radiate.
It's a stealth mode.
In a way. The internal fields are bouncing around furiously, but the boundary conditions are such that nothing leaks out. It becomes a resonant cavity made of its own plasma. He compares it to the field inside a perfectly conducting metal sphere, but here, the plasma itself creates the confinement. If you get the size and the frequency to match perfectly, the outward radiation cancels out. It becomes invisible to the outside world, electromagnetically speaking.
That sounds incredibly difficult to achieve in nature. I mean, what are the odds of a lightning strike creating a plasma ball that is exactly the right radius to satisfy a Bessel function 0?
That is the million-dollar question. And Nachamkin acknowledges this. He admits that generating these things is a puzzle. However, nature has a way of finding energy minimums. If this state, this force-free, resonant state, is a low-energy valley in the landscape of physics, a chaotic event like a lightning strike might just stumble into it. The system might naturally evolve toward that stability because it's the path of least resistance.
So it's not that the lightning aims for the Bessel function, it's that any plasma ball that doesn't hit that resonance dies instantly, and the ones we see, the rare ball lightning cases, are the ones that happen to lock into that frequency.
Exactly, survivorship bias of plasma physics. And looking at the numbers in the report, they are striking. He calculates an example for a 10-centimeter plasmoid, about the size of a grapefruit. He suggests it could contain a megajoule of energy.
A megajoule, that's a stick of dynamite, roughly.
It's a lot of energy for a grapefruit, and that aligns with some of the more frightening reports of ball lightning, where they melt windows or boil water barrels. The density of energy Nachamkin's model predicts is consistent with those observations. He mentions that for a 20-centimeter diameter plasmoid in standard atmosphere, the trapped radiation would be in the gigahertz range, microwaves, basically.
So it's a floating microwave oven.
A floating, self-contained microwave oven that is also a tornado. Remember the fluid dynamics part? He talks about the vortical plasma stabilization. The electromagnetic pressure pushes out, but the swirling motion of the gas creates a low pressure zone, like the eye of a storm, that sucks it back in. The math shows these two forces can balance almost perfectly.
I want to go back to something you mentioned earlier about the vactoid. There's a section in the report where he talks about a vacuum plasmoid. Is he saying you could have this structure without any plasma at all? Just pure trap light?
That is the most speculative and mind-bending part of the paper. He calls it a vactoid or a vacuum plasmoid. Mathematically, at a specific critical frequency, the charge density and current density terms drop to 0. The equations still hold, but there's no stuff there. It implies you could theoretically have a packet of electromagnetic energy trapped in a spherical region in a vacuum, held together by its own geometry and boundary conditions.
That sounds like a photon torpedo, or a ghost. If there's no matter, what is it?
Classically, it would be almost undetectable. It creates no external field. It has no charge, but it has mass, because energy is mass, E equals mc squared. So it would have gravity. Nachamkin suggests that unless you hit it with something ionizable, you wouldn't even know it was there. But he also admits this is likely apocryphal, a mathematical ghost rather than a physical reality, because you'd need impossibly specific surface currents to bound it. But the fact that the math allows for a ball of light, independent of matter, is pretty wild.
It is wild, but let's ground this back in the main theory. We have this model: force-free magnetic fields, resonant frequencies, vortical flow. It's been 30 years since this report. Has anyone actually built one of these?
Well, we haven't seen a commercial plasmoid battery on the shelf yet, but the concepts here are foundational to the spheromac reactors used in fusion research.
The spheromac is a type of magnetic confinement device that uses these force-free currents to hold the plasma together without the heavy external magnets used in tokamaks. They haven't achieved the perfect self-sustaining stability Nachamkin describes for long durations, but the principle of the force-free state, where the plasma relaxes into that low-energy twist, is widely accepted in plasma physics now. This report was really ahead of its time in trying to synthesize the fluid dynamics with the electromagnetics.
There's a tension in the report, though. He keeps bringing up the issue of drift. The electrons have mass. They aren't massless points. So when they try to follow these curved magnetic field lines, they drift off course. Doesn't that ruin the whole force-free perfection?
It does, and that's the dirty reality of physics versus math. In an ideal world, electrons flow perfectly along the lines. In reality, they have inertia. They swing wide on the turns. This drift creates currents that don't fit the model, which create fields that radiate energy, and the whole thing destabilizes. Nachamkin addresses this by saying the electric field has to be kept below a certain limit relative to the radius to keep the drift manageable. It basically puts a speed limit on how much energy you can pack in before the electrons drift too much and break the containment.
So it's a balancing act. Too much energy, the electrons drift and break the bottle. Too little frequency, the bottle isn't rigid enough to hold its shape. It seems like the window for this to exist is tiny.
It is tiny, but again, look at ball lightning. It's incredibly rare. Most people never see it. It lasts a few seconds, maybe a minute. That fits perfectly with a phenomenon that exists in a tiny, unstable window of physical parameters. The fact that it exists at all is the miracle. Nachamkin's model gives us a roadmap for why it might be possible, even if it's improbable.
I notice he also talks about the viral theorem. I always get tripped up on this one. What role does the viral theorem play here?
The viral theorem is basically a sanity check for stability. It relates the kinetic energy of a system, the movement of the particles, to the potential energy, the forces holding them together. For a system to be stable and bound, meaning it doesn't fly apart, the viral theorem has to be satisfied. Usually, for a ball of charge, the viral theorem says no way. This explodes. Nachamkin uses a virial analysis to show that under his specific conditions, the high frequency, the force-free fields, the terms balance out to zero. The time-averaged moment of inertia doesn't grow. It proves that, at least mathematically, the expansion forces are completely negated by the confinement forces.
It's the mathematical proof that the impossible is possible. I want to zoom out a bit. We're talking about a report from 1992. But the language he uses, he talks about undiscovered and as yet unknown principles possibly being involved. He mentions quantum electrodynamics, QED, and the zero-point field. Is he suggesting that classical physics isn't enough to explain this fully?
He's leaving the door wide open. He says explicitly that while he's presenting a classical model using standard Maxwell's equations and Newton's laws, it might not be the whole story. He hints that for very small, high-energy plasmoids, you might need to look at vacuum polarization or zero-point energy effects. That's where you get into the fringe science of extracting energy from the vacuum, which Puthoff, who is cited in the references, is famous for. Nachamkin is being a rigorous scientist here. He's saying, here is how far classical physics gets us, and it gets us pretty far, but there are dragons at the edges of the map.
It's interesting you mentioned the references. He cites Bostick, who coined the term plasmoid, and he cites Kapitsa, a Nobel Prize winner who also thought ball lightning was a standing wave. But he also cites Puthoff. It's a mix of mainstream Nobel science and the edges of speculative physics. It feels like this report exists in a liminal space.
That's a great way to put it. It's a bridge document. It takes the hard-nosed, military-funded engineering requirements of the Air Force and applies them to a mystery that borders on the paranormal. But the rigor is undeniable. The appendices in this report are thick with vector calculus. He's not just hand-waving. He's deriving these fields from first principles. He essentially proves that if you can get the geometry right, the physics allows for these ghost structures of energy.
Let's talk about the conclusion. He outlines a recipe for making these things. He says, 1, create a spherical vortex. 2, maintain ionization. 3, pump it with electromagnetic energy. It sounds like instructions for a mad scientist. Do you think we could build a generator for these?
People are trying. There are experiments with plasma vortex rings, and there are experiments using microwaves to sustain plasma balls in cavities. The Japanese researchers he mentions have done exactly that. Create long-lived plasmoids in microwave cavities. The tricky part is the autonomous part, getting it to survive outside the cavity without the external power source. Nachamkin suggests that the plasmoid needs to have a column of current traversing it to pump it initially. Imagine a lightning bolt, the column, passing through a swirling vortex of air, dumping its energy into that specific resonance, and then the bolt vanishes, leaving the spinning, humming ball behind.
That visual is incredibly clear. It explains why ball lightning is often seen after a strike. The strike is the charging cable. The ball is the battery that gets left behind.
Exactly. And if that battery is force-free, it doesn't leak. It holds that charge until something disrupts the balance, it hits a wall, the temperature changes too much, or the frequency drifts, and then pop. All that megajoule energy releases at once.
Which explains the reports of them exploding like bombs. So, Eloise, final thoughts on this report. Is it just a historical curiosity, or is there something here we still haven't unlocked?
I think it's a dormant seed. We currently rely on brute force for fusion, huge magnets, massive lasers. This report suggests a path of elegance, using the plasma's own behavior to confine itself. If we can master the force-free modes Nachamkin describes, really master them, it could revolutionize how we store energy. Imagine a battery that isn't chemical, but a tiny suspended star of pure electromagnetic structure. We aren't there yet, but the math says it's not impossible.
A tiny suspended star. I like that. It reminds me that sometimes the most advanced technology is just catching up to what nature does by accident during a thunderstorm. This report by Nachamkin is a dense mathematical forest, but hidden inside is a blueprint for something pretty spectacular.
Imagine you're trying to hold a sphere of jelly together, but you can't touch it with your hands. You can only use rubber bands. And the jelly isn't just sitting there, it's vibrating, expanding, and actively trying to squirm out of your grip. Now, heat that jelly to 100 million degrees. It's not jelly anymore. It's the fourth state of matter, plasma. And if it touches the rubber bands or the walls of your room, the whole thing vanishes in a puff of cooling gas. That is the nightmare of fusion energy. We've been promised a star in a jar for 70 years, but it turns out the star really doesn't want to be in the jar. I'm Jake, and today we're bypassing the hype to talk about the single hardest engineering challenge in human history, the stability of plasma. Specifically, we're asking why the mainstream approach, the giant magnetic donut known as the tokamak, is struggling, and why a rebellious group of physicists thinks the answer lies in something called plasmoid theory. Joining me is Rachel, who has been tracking the collision between government megascience and the private fusion industry. Rachel, welcome.
It's good to be here, Jake, and that jelly analogy is actually frighteningly accurate.
It feels like we're constantly hearing fusion is just around the corner. But when you look at the big projects like ITER in France, the timeline keeps slipping. Is plasma just impossible to control?
It's not impossible, but it is chemically malicious. We have to start with what plasma actually is. When you heat a gas enough, the electrons get stripped off the atoms. You're left with this soup of charged particles, ions and electrons. Because they're charged, they respond to magnetic fields. That's the key. The mainstream theory, the one that's dominated since the 1950s, is magnetic confinement. You build a magnetic cage. If the magnetic field is strong enough, the particles spiral around the field lines and never touch the walls. In theory, you trap the heat, the atoms fuse, and you get clean energy.
Right, and this is the tokamak design, the donut.
Exactly, the tokamak. It was invented by Soviet physicists Igor Tamm and Andrei Sakharov in the 1950s. The idea is to create a torus, a donut shape. You wrap huge electromagnetic coils around the outside. These external magnets squeeze the plasma into a thin ring floating in the center of the vacuum chamber.
It sounds elegant. So why is it so hard?
Because plasma isn't a solid fluid like water, it's an electrically conductive fluid that generates its own magnetic fields as it moves. So you have the external magnets trying to push it in, and the plasma creating internal currents that push back. This creates what we call instabilities. And they have fantastic names. There's the sausage instability, where the plasma stream starts to bulge and pinch like links of sausages until it snaps. There's the kink instability, where the plasma beam twists itself into a corkscrew and hits the wall.
So it's like the plasma is actively looking for the weak point in the cage.
It essentially is. In a tokamak, if the plasma hits the wall, you get a disruption. The heat dumps into the wall, the plasma cools down instantly, and the reaction dies. Worse, it can melt the machine. That's why devices like ITER are so massive. They are building a cathedral-sized machine just to keep the plasma stable for a few minutes.
And that's the criticism, right? That tokamaks are becoming dinosaurs? I read that ITER is now billions over budget and decades behind schedule.
That's the economic critique, yes. But there's a physics critique too, and it centers on a number called beta. This is really important.
Okay, break down beta for us.
Beta is the ratio of plasma pressure to magnetic pressure. In simple terms, how much fusion bang are you getting for your magnetic buck? A tokamak has very low beta, usually around 5% or less. That means you need massive, expensive, power-hungry magnets to hold a tiny amount of wispy plasma. It's like building a bank vault to hold a single dollar bill.
So you're spending all your energy and money on the cage, not the animal inside.
Precisely. And this is where plasmoid theory enters the chat. The proponents of plasmoids asked a radical question. What if we don't need the external cage? What if the plasma could be its own cage?
That sounds like pulling yourself up by your bootstraps. How can a gas hold itself together?
Think of a smoke ring. You've seen how a smoke ring can travel across a room, holding its shape, spinning on itself? That is a self-organized structure. The air is rotating in a way that creates a container for itself. A plasmoid, specifically something called a field-reversed configuration, or FRC, is the plasma version of a smoke ring. You induce a current inside the plasma. That electrical current generates a magnetic field that wraps around the plasma and holds it together. It's a self-contained magnetic bottle.
So in the tokamak, the magnets are on the outside looking in. In a plasmoid, the magnets, or rather the magnetic fields, are generated by the plasma itself.
Correct. And because the field comes from the plasma, the beta is incredibly high. We're talking nearly 100% beta. The magnetic pressure and the plasma pressure are almost equal. This means you don't need those cathedral-sized external magnets. You can build a reactor that fits on a truck, theoretically.
This sounds too good to be true. If we've known about smoke rings and plasmids for decades, why hasn't ITER still building the giant donut? Why hasn't this one yet?
Because while plasmoids are efficient, they are notoriously suicidal. A smoke ring looks stable, but eventually it dissipates. FRCs have historically been very short-lived. They tend to tilt, wobble, and decay in microseconds. The challenge shifted from how do we build a big enough cage to how do we keep this smoke ring spinning fast enough to fuse before it falls apart.
This brings us to the modern private sector, doesn't it? Companies like Helion and TAE Technologies. They aren't using the government tokamak approach. They're betting on plasmoids.
They are, and they're doing it by changing the game from sustained to pulsed. The tokamak wants to burn steady, like a gas stove. Helion, for instance, is treating fusion more like a diesel engine. They create two plasmoids, two of these magnetic smoke rings, at opposite ends of a long tube.
Like loading two bullets into a gun barrel.
Exactly. They use magnets to accelerate these plasmoids toward each other at over 1 million miles per hour. They smash together in the center. That collision compresses them, heats them up, and for a tiny fraction of a second, you get fusion.
So they don't care if the stability lasts forever. They just need it to last long enough for the crash.
Right. It's a pulsed system. Bang, fusion, energy out. Then you reload and do it again. Helion aims to do this once per second. The brilliant part, and this is unique to plasmoids, is how they get the electricity out.
This is the induction thing, right? No steam turbines.
Yes, and this is a massive differentiator. In a tokamak, the fusion creates heat, the heat boils water, the steam spins a turbine. It's 19th century technology racked around 22nd century physics. But because a plasmoid is a ball of magnets, when it expands after the fusion explosion, it pushes back against the machine's magnetic field. Faraday's law of induction takes over. The changing magnetic field induces a current directly in the coils. They capture electricity directly from the plasma. No steam, no turbines.
That feels like the iPhone moment for energy if it works, going from analog steam to digital direct capture. But you mentioned if it works. What are the critics saying? Because I see Helion signing deals with Microsoft to provide power by 2028, which is astonishingly soon.
The skepticism is warranted. The critics, mostly from the tokamak community, point out that we have never achieved a net energy gain from a plasmoid system yet. The confinement times are still very short. There are worries about the wall materials. When you smash plasmoids that hard, you're blasting the walls with neutrons and X-rays. Can the machine survive running 24/7 for years?
It's the difference between building a rocket and building a car engine. A rocket works once. A car engine needs to fire millions of times without cracking.
And there's the fuel issue. Helium wants to use helium-3 and deuterium because it produces fewer neutrons. It's cleaner. But helium-3 is incredibly rare on Earth. They actually have to breed it inside the reactor using side reactions. It adds a layer of complexity that the tokamak guys, who generally plan to use tritium, think is unnecessary risk.
But looking at the history here, the tokamak has had 70 years and billions of dollars. The plasmoid approach was sort of left in the cold after the 1970s, wasn't it?
It was. In the late 70s and 80s, the US government basically decided to put all its chips on the tokamak because it seemed the most scientifically mature. They defunded the alternative concepts like the FRC and the Spheromac. What we're seeing now is a renaissance of those lost ideas funded by Silicon Valley billionaires rather than the Department of Energy.
It's interesting how the architecture of the machine reflects the philosophy of the builder. The tokamak is this centralized, government-scale, steady-state beast. The plasmoid reactor is modular, pulsed, smaller, potentially mass-manufactured.
That's the key appeal. If you can make a plasmoid reactor work, you don't build it on site like a nuclear power plant. You build it in a factory and truck it to the data center or the factory that needs power. That is why Tay Technologies and Helion are attracting so much capital.
Let's dig a bit deeper into Tay Technologies because they have a slightly different flavor of this plasmoid idea, right?
Right. TAE, which stands for Tri-Alpha Energy, uses a device called Norman. They also use field reverse configurations, so they are Team Plasmoid. But instead of just crashing them and hoping for the best, they use neutral beams, high-energy particle beams, to keep the plasmoid spinning. Imagine spinning a top. Eventually, friction slows it down and it wobbles and falls. TAE fires beams at the edge of the plasma to kick it, keeping it spinning. They've managed to keep FRCs stable for significantly longer periods using this active control.
So they are trying to fix that wobble we talked about earlier, the tilt instability. Exactly. If they can stabilize it long enough, they want to use hydrogen and boron fuel. That is the holy grail of fuels, because it produces almost no radiation. But it requires temperatures of billions of degrees, not just millions. You can only get there if your confinement is perfect.
I want to circle back to the why now question. If these ideas existed in the 60s, why didn't they work then? Is it just better magnets?
It's magnets, but it's mostly computing. Controlling plasma is a feedback loop. The plasma moves, a sensor sees it, a computer calculates the correction, and a magnet fires to push it back. In the 1980s, computers were too slow. The plasma would crash before the computer even knew it had moved.
Today, we have AI and modern control systems that can react in nanoseconds. We can fly the plasma like a fighter jet. We also have high-temperature superconductors, magnets that are much stronger and smaller than anything the Soviets had in the 50s. That hardware revolution is what makes the high-beta plasmoid approach viable today.
It really highlights that fusion isn't just a physics problem anymore, it's a control systems problem.
So, Rachel, if you had to bet, we have the incumbent, the tokamak, big, reliable science, but slow and expensive, and the challenger, plasmoids, high risk, high efficiency, pulsed, who gets to the grid first.
If we are talking about putting actual electrons on the commercial grid, I'd lean toward the private plasmoid companies simply because they can iterate faster. They can build a machine in 2 years, break it, and build a new one. ITER is taking 30 years to build one machine. In engineering, iteration speed usually wins. However, the physics of the tokamak is better understood. We know a tokamak can fuse atoms. We proved that at the JET lab in the UK. We haven't definitively proven that a plasmoid generator can produce net electricity yet, so the plasmoid path is a gamble, but it's a gamble with a much higher payout if it hits.
And the implications of that payout are staggering. Stable plasmoids mean decentralized, clean power without the nuclear waste profile of fission.
It changes
everything. And the irony is, it might happen because we stopped trying to put the star in a jar and started letting the star build its own jar.
Beautiful way to put it. The universe loves self-organization, from galaxies to smoke rings. Maybe our energy should follow suit.
Today we're diving into a fascinating concept from a 1992 paper by Jack Nachamkin titled Force-Free Time-Harmonic Plasmoids. This work explores a novel solution to Maxwell's equations, suggesting that electromagnetic energy can be trapped in a stable, spherically symmetric form. Eloise, to start, the paper talks about plasmoids and force-free fields. Can you demystify what those terms mean in this context?
Certainly, Noah. At its heart, Nachamkin's paper defines a force-free field as one where a vector field, let's call it F, is proportional to its own curl. Mathematically, this is expressed as curl F equals alpha F, where alpha is a constant. For something like a magnetic field, this means the field lines essentially curl back on themselves in a very specific way. In such a field, the usual stresses that would act on currents are minimized, which is where the force-free name comes from. The origin of the name comes from the observation that for a DC magnetic field, satisfying this condition in vacuum, the current field required to sustain it would be parallel to the magnetic field, meaning the Lorentz forces on the current would be nil.
And a plasmoid, then, is this trapped electromagnetic energy?
Precisely. A plasmoid, as Bostic described it, is a structure made of plasma whose form is determined by the magnetic field it carries. Nachamkin builds on this by proposing a theoretical model where these stable, long-lived spherical plasma structures are sustained by a combination of force-free electromagnetic fields and a matching vortical fluid motion within the plasma itself. The overall model is a combination of a time-harmonic force-free electromagnetic field and a matching vortical fluid motion, neither of which could exist stably on its own.
So it's not just a magnetic field, but also an electric field and a current, all in this force-free configuration. That sounds inherently unstable, especially if we're talking about electromagnetic energy being trapped without dissipation. How can such a thing exist without just radiating away or falling apart?
That's the core challenge Nachamkin addresses. Classically, these fields can't exist in a vacuum without boundary currents. In a quiescent plasma, internal stresses usually disrupt them. But the paper introduces a critical frequency, which is determined by the plasmoid's size. Above this critical frequency, the current can be carried by electrons, and the plasma state shifts to an energy minimum, which is much more stable, meaning the magnetic interaction energy becomes negative.
A critical frequency where stability changes? How does that work on an energetic level?
Well, above this critical frequency, the interaction energy between the current and the magnetic field becomes negative. This is counterintuitive, but it means that small perturbations to the current actually increase the total energy of the system. Imagine it like a stretched elastic band. If you try to deform it, it wants to snap back to its stable state. This elastic behavior lends a degree of stability to the plasmoid. Below this critical frequency, the system is at a local energy maximum and is unstable to perturbations.
That's a powerful analogy. And how does the issue of radiation fit in? If energy is trapped, why isn't it leaking out?
This is another crucial point. Nachamkin shows that if the plasmoid has a resonant size, a specific radius tied to its internal wavelength, the electric and magnetic fields at its surface can be perfectly tangential. This means they are aligned with the surface, not pointing outward. Consequently, such a plasmoid will not exchange energy with its external surroundings, and its boundary conditions can be met by vacuum solutions to Maxwell's equations without surface currents. This drastically reduces outward-going radiation. The analogy here is to a TE resonance in a spherical cavity.
Geometry and specific frequency create this perfect seal in a way, but the abstract also mentions electromechanical stresses and vortical motion. Where did these come into play?
This is where the model gets even more intriguing. The electromagnetic fields within the plasmoid induce stresses, particularly a pressure field proportional to the square of the electric field, which acts like an outward pressure. This would normally cause the plasmoid to expand and dissipate. However, Nachamkin shows that this stress can be almost perfectly balanced by a stable, vortical fluid motion within the plasma, known as Beltrami motion. This vortical motion creates a pressure field that cancels the electromagnetic pressure.
So the plasma itself starts to swirl,
And that swirling motion counteracts the internal pressure from the electromagnetic fields. It's a self-stabilizing dynamic.
Exactly. The velocity field of this vortex also has a force-free form, making it remarkably compatible with the internal stresses. This combination means that the force-free time-harmonic electromagnetic field and the matching vortical fluid motion, neither of which could exist separately in a stable way, come together to create a long-lived, high-energy density plasmoid. The residual stress, after cancellation, is just a uniform pressure.
The paper mentions this model might explain phenomena like ball lightning or charge clusters. Are these just theoretical applications, or is there experimental evidence backing this up?
Nachamkin does suggest these are potential applications. He notes that experiments in the late 1960s and early 1970s at Los Alamos, related to fusion weapons and laser fusion, observed anomalies like unexplained symmetries in disintegrating pellets and puzzles about plasma compression instability. He also points to ongoing observations of ball lightning and charge clusters in strong plasma discharges as phenomena that might, at least in part, be described by this theory. He even gives a numerical example in the appendix of a 1 megajoule force-free plasmoid in an STP atmosphere that could be described with physically reasonable parameters.
1 megajoule in a 10-centimeter sphere is quite impressive. But if this model is so robust, why aren't we seeing these plasmoids everywhere or reliably creating them in labs?
That's the remaining challenge. Nachamkin acknowledges that while the theory doesn't violate any physical principles, it's not immediately obvious how one would go about producing them. He outlines 3 necessary steps: producing closed spherical vortices, maintaining desired ionization levels, and generating electromagnetic energy at the critical frequency within the plasmoid. Essentially, you'd need a very strong discharge in an ionizable gas, perhaps with a high-frequency electromagnetic field, to initiate a pinch effect, which then turns into a swirling vortex that traps the field.
So it's a grand vision of self-contained energy packets, potentially explaining some natural mysteries. The key is in that precise interplay of the electromagnetic forces and the fluid's motion to achieve this delicate balance.
That's exactly right. The unique aspect is this remarkable coincidence where a non-propagating electromagnetic field and a specialized vortical fluid field, both having the same functional form, combine to produce a stable, high-energy density entity that neither could maintain on its own. The theory as presented is incomplete, leaving open questions about quantum effects and interactions with the zero-point background.
This has been a fascinating look into the theoretical possibility of stable, force-free plasmoids.
Okay, picture this. You are trying to hold on to a cloud of gas, but not just any gas. We're talking about hydrogen heated to 100 million degrees. It's frantic, it's violent, and it wants to expand, explode, and touch literally anything other than itself. If it touches the walls of your container, it cools down instantly and your fusion reaction dies. If it stays hot, it melts the walls and your machine dies. That is the fundamental paradox of fusion energy. So, for the last 70 years, the solution has been what I call the zoo approach. You build a massive, heavy, incredibly expensive cage. You surround this gas with gigantic external magnets, superconducting coils that weigh tons, and you force the gas into submission. You squeeze it from the outside in. That's the tokamak. That's the big donut-shaped reactor they're building in France right now. But there is another way, a stranger way. What if you didn't need the cage? Or more accurately, what if the prisoner built its own jail cell? What if the gas, the plasma itself, could flow in such a specific, self-organized pattern that it created its own magnetic field, locking itself in place, holding itself together against the vacuum, with almost no help from the outside? It sounds like magic, like a tornado that decides to stand still and hold up a roof, but it's real physics. It's called a field reverse configuration, or FRC, and depending on who you ask, it is either the most frustrating instability in plasma physics or the holy grail that is finally going to give us clean, infinite energy. Today, we are doing a deep dive into the FRC. We're going to look at how a gas forms its own cage, why the mainstream science community ignored it for decades, and why a couple of billion-dollar startups think this weird self-stabilizing smoke ring is going to save the world. Part 1. The Ghost in the Machine. To understand the FRC, we have to go back to the Wild West of fusion research, the late 1950s. This was before we had settled on the tokamak as the chosen one of reactor designs. Back then, scientists were throwing everything at the wall to see what stuck. And one of the most popular devices was something called a theta pinch. Now, a theta pinch is exactly what it sounds like. Imagine a glass tube wrapped in a copper coil. You fill the tube with gas, and then you slam a massive pulse of electricity through that coil. The coil creates a magnetic field that squeezes the gas, pinches it inward really fast. Ideally, you squeeze it so hard and so fast that it gets hot enough to fuse. But something weird started happening in these experiments. The researchers noticed that sometimes if they set up the magnetic fields in a very specific way, specifically if they had a background magnetic field going one way, and then they pulsed a new field going the opposite way, the plasma wouldn't just squeeze, it would tear itself off from the walls and curl up. It formed a closed loop, a torus, a donut. But unlike the donuts we see in modern reactors, which need a metal pole running through the middle to keep them stable, this donut had nothing in the center. It was just a floating ring of plasma, spinning and holding its shape. And here's the kicker. It was reversing the magnetic field inside itself. That's where the name comes from, field reversed configuration. The magnetic field lines from the outside pointed north, let's say, but inside the spinning ring of plasma, the current was moving so fast that it generated its own field pointing south. It dug a magnetic hole in the universe and sat inside it. At the time, this was baffling. In standard magnetohydrodynamics, that's the physics of electrically charged fluids, this thing shouldn't have been stable. It should have flipped over or torn itself apart in microseconds. But in some of these early experiments, it just sat there. Well, for a few hundred microseconds, which in plasma time is an eternity. It was like finding a smoke ring that refuses to dissipate. You know when you blow a smoke ring, it holds its shape as it travels across the room. That's a vortex. The air is rolling over itself, creating a barrier that separates the ring from the still air around it. An FRC is basically a magnetic smoke ring. It is a self-organized structure. But history took a turn. The tokamak design, which was invented by the Soviets, offered better confinement time. It was more predictable. It was safer in a physics sense. The tokamak is a low-pressure beast. You use massive magnets to hold a very wispy, low-pressure plasma. It's like keeping a butterfly in a bank vault. The FRC, on the other hand, was high-pressure, chaotic, and hard to control. So by the 1970s and 80s, the big government funding mostly shifted to tokamaks. The FRC became a niche interest, a curiosity kept alive by a few die-hard labs. Part 2. The smoke ring and the cage. So let's get under the hood. How does a gas actually build a cage? How does this work without the bank vault? You have to understand the difference between beta in finance and beta in plasma physics. In fusion, beta is the most important number you've never heard of. It is a ratio. Specifically, it's the ratio of the plasma's internal pressure pushing out versus the magnetic field pressure pushing in. In a standard tokamak reactor, the beta is low, like 5% or less. That means the magnetic cage is 20 times stronger than the plasma inside it. The cage is doing all the work. The plasma is just a passenger. In an FRC, the beta is close to 1. That is unity. That means the pressure of the plasma is almost equal to the pressure of the magnetic field. The plasma isn't a passenger anymore, it's the driver. The electrical current running through the plasma, which is just the flow of the ions and electrons themselves, is what generates the magnetic field that confines it. Think of it like a woven basket. If you weave a basket out of flexible reeds, the basket holds its shape because of the tension in the reeds. In an FRC, the plasma particles are the reeds. They're zooming around in a circle, and that motion creates a magnetic current. The Ampere's law stuff for the physics nerds out there. That current creates a magnetic field that wraps around the plasma, squeezing it. So the faster the particles move, the stronger the cage becomes. This leads to a really interesting geometry. If you look at a tokamak, it looks like a donut, but it has a hole in the middle where the central solenoid, a big magnet, goes. An FRC is a compact toroid. It's still technically a donut topology, but it's a donut without the hole. Imagine if you took a donut and squished it until the hole disappeared, or like a cored apple where the core is just magnetic flux. It looks more like a sausage or a cigar floating in the chamber. This shape is incredibly efficient. Because you don't need that giant magnet in the center, the reactor can be much smaller. It's just a simple cylindrical tube. This is why startups love it. You don't need a building the size of a cathedral to house it. You can stick a linear tube in a warehouse. But there's a catch. There's always a catch. When you let the prisoners run the prison, things can get rowdy. The FRC is a delicate balance. It's like balancing a broomstick on your palm. It wants to fall over. Part 3. The wobble. So why don't we have FRC reactors powering our cities yet? If they're smaller, cheaper, and self-organizing, what's the holdup? The holdup is that they are notoriously unstable, and not just, oops, it turned off unstable. I mean violent geometric distortion unstable. There are two main ways an FRC tries to die. The first is called the tilt instability. Remember, the FRC is a magnetic dipole. It has a north and a south pole, created by its own current. It's floating inside an external magnetic field. Now, if you've ever played with two bar magnets, you know that if you try to hold them north to north, they want to flip. They want to align. The FRC is the same. It wants to flip over 180 degrees to align with the external field. If it tilts, it hits the wall. Game over. The second killer is the rotational instability. As the plasma spins, it can start to deform. It goes from a nice circle to an oval, then to a peanut shape, and then it tears itself apart. It's like a pizza dough that you spin too fast. Eventually, it gets too wide and rips. For decades, the theory said these instabilities were impossible to stop. The math, specifically a type of math called MHD, magnetohydrodynamics, predicted that an FRC should tilt and die in microseconds. But here is the fascinating thing. The experiments kept defying the math. The real FRCs were living longer than the equation said they should. It turns out the FRC has a secret weapon. It's called kinetic stabilization. See, MHD treats plasma like a fluid, like water. But plasma isn't just water, it's a collection of individual particles. In an FRC, the magnetic field is zero right in the center, the null point. Because the field is weak there, the ions, the heavy nuclei, have huge orbits. They don't just spiral tightly like they do in a tokamak. They take big, wide, meandering paths that swing in and out of the core. These large orbits act like a gyroscope. You know how a spinning top doesn't fall over? It's because the angular momentum keeps it upright. The fast-moving ions in an FRC act like the rim of that spinning top. Their individual motion averages out to stabilize the whole structure. The fluid model couldn't see this, but the particles knew what they were doing. Part 4. The billion-dollar bet. This brings us to the modern era. We are currently seeing a renaissance of the FRC, driven not by governments, but by private capital. There are two big names you need to know here. TAE Technologies, formerly Tri-Alpha Energy, and Helion Energy. These companies looked at the Tomahawk, the slow, expensive, low beta approach, and said, no thanks. They bet the farm on the FRC. Let's look at TAE first. Their machine, which they've iterated on for years, one version was called Norman, creates an FRC and then shoots high-energy beams of neutral particles at it from the side. Imagine spinning a top and then using a leaf blower to keep it spinning. That's what the neutral beams do. They inject energy and current to keep the FRC spinning and stable, fighting off that tilt instability. Then you have Helion. Their approach is even more aggressive. They don't just want to sustain the FRC, they want to crash it. They form two FRCs, two smoke rings, at opposite ends of a long tube. They use magnets to accelerate them toward each other at 1,000,000 miles an hour. They smash them together in the center. The collision merges them into one superhot FRC, which they then compress with a magnetic pulse. Helion isn't trying to keep the FRC alive forever. They just need it to live long enough to burn. It's a pulse system. Bang, fuse, extract energy. Repeat. It's like a diesel engine piston, but instead of compressing air and fuel, you're compressing a magnetic smoke ring. Why go through all this trouble? Why deal with the wobbles and the tilts? Because if you can make the FRC work, you unlock the holy grail of fuels and neutronic fusion. Standard fusion uses deuterium and tritium. It releases high-energy neutrons that are dangerous and make the machine radioactive. But because FRCs have such high beta, remember high pressure, they can theoretically reach much, much higher temperatures, hot enough to burn exotic fuels like hydrogen boron or helium-3. These fuels don't release neutrons. They release charged particles. And this is the killer app. If your fusion reaction releases charged particles, you don't need a steam turbine. You don't need to boil water to spin a generator. You can use the magnetic field of the expanding plasma to generate electricity directly in the coils. It's called direct energy conversion. It's elegant, it's efficient, and it is only possible if you can master the self-organizing cage of the FRC. So, where are we now? Well, it's a race. The private companies are claiming massive progress. They're hitting temperatures of 70, 100 million degrees. They've proven that the flow stability isn't a dead end, that the kinetic effects really do work. But sustaining it for long durations or pulsing it fast enough to make net electricity is still an engineering mountain to climb. It's easy to be skeptical. Fusion is always 20 years away, right? But the FRC represents a fundamental shift in how we think about control. The tokamak represents the old human impulse: dominate nature, build a wall, force it to obey. The FRC represents a different philosophy: cooperation with nature. It acknowledges that plasma wants to flow, it wants to turn, it wants to organize. Instead of fighting that tendency, the FRC uses it. It asks the gas to build its own cage. And there is something poetic about that. The idea that the most chaotic substance in the universe, left to its own devices, doesn't just descend into disorder. It seeks structure. It seeks stability. It spins itself a cocoon. If we can harness that, if we can learn to dance with the plasma rather than wrestle it, we might just light up the world.
Imagine a fire that doesn't produce smoke. It doesn't leave behind ash. It doesn't even heat a boiler to make steam. Instead, the flames themselves, which are actually electrically charged particles, push directly against a magnetic field to create electricity. No steam turbines, no meltdown risk, and virtually no radioactive waste. That is the promise of exotic fusion.
But there's a catch, right? There's always a catch, because usually when we talk about fusion, we're talking about massive government projects, billions of dollars, and the running joke that it's always 30 years away. But today, we aren't talking about the standard approach. We're looking at the rebels of the physics world.
Exactly. We're moving beyond the Model T of fusion fuels, deuterium and tritium, and looking at the high-performance stuff, helium-3 and hydrogen boron. This is the realm where sci-fi meets hard engineering, where we talk about mining the moon and heating plasma to temperatures hot enough to make the center of the sun look chilly.
Welcome to the deep end of energy physics. I'm Chloe.
And I'm Alex.
So, Alex, let's set the stage. Most of us have a vague idea of fusion, smashing atoms together to release energy like the sun does. But you're telling me that the fusion everyone is trying to build right now, projects like ITER in France, might actually be using the wrong fuel?
I wouldn't say wrong, but certainly difficult. See, for 70 years, the scientific community has focused almost exclusively on one specific reaction: deuterium tritium, or DT.
Why that one?
Because it's the easiest to ignite, and I use easy in massive air quotes here. You only need to heat it to about 150 million degrees Celsius. In the world of nuclear physics, that's considered low-hanging fruit. Deuterium is found in seawater, and tritium is a radioactive isotope of hydrogen. When they smash together, they release a lot of energy. But they have a dirty little secret.
Which is?
Neutrons. The DT reaction releases 80% of its energy as high-energy neutrons. These are neutral particles, so you can't contain them with magnetic fields. They fly out of the plasma like microscopic bullets and smash into the walls of the reactor.
I've heard this described as the material science nightmare. It makes the reactor walls radioactive, right?
Precisely, it causes neutron activation. The steel and concrete eventually become low-level radioactive waste. Plus, those neutrons degrade the structural integrity of the machine. But the real inefficiency is how we harvest that energy. Since the neutrons carry the energy as heat, we have to let them hit the wall, get the wall hot, boil water, make steam, and spin a turbine.
So we're building a miniature star just to boil a kettle.
That is the great irony of DT fusion. It's 22nd century physics hooked up to 19th century steam technology. And that is where exotic fuels, what we call aneutronic fuels, change the game completely.
Aneutronic meaning no neutrons?
Or very, very few. The two big contenders here are deuterium helium-3 and proton boron 11. These reactions produce charged particles, protons and alpha particles, instead of neutral neutrons.
Okay, hold on.
why does the charge matter?
Because if a particle has a charge, you can control it with magnets. You don't have to let it smash into a wall to create heat. You can use magnetic fields to decelerate these particles, converting their kinetic energy directly into electricity. It's called direct energy conversion. Think of it like regenerative braking in an electric car, but for plasma particles.
That sounds incredibly elegant. You skip the steam, the turbine, and the radioactive walls. So why aren't we doing this everywhere? Why is ITER still messing around with tritium?
2 reasons. The fuel is hard to get, and the fire is hard to light. Let's start with the fuel, specifically helium-3. It's often called the holy grail of fusion. It's a stable isotope of helium, but it's missing a neutron.
I feel like I've heard about this in movies. Isn't this the plot of the movie Moon?
It is, and there's some truth to it. Helium-3 is incredibly rare on Earth. It's mostly formed by the decay of tritium, which, as we mentioned, is used in nuclear warheads. So unless you have a stockpile of nukes, you don't have much helium-3. In fact, the U.S. supply is tiny, mostly used for neutron detectors at borders.
But the Moon has it?
Yes, the sun constantly blasts the solar system with solar wind, which is rich in helium-3. Earth has a magnetic field that deflects it, but the Moon doesn't. So for billions of years, the lunar soil, the regolith, has been soaking up helium-3 like a sponge. Estimates suggest there are over 1 million tons of it up there.
Okay, but let's be real. Mining the Moon? We're struggling to fix potholes on I-95. Is that actually a viable economic strategy for energy?
It's a controversial point. The economics are aggressive. You'd have to process millions of tons of lunar soil just to get a shuttle load of gas. While technically possible, building a lunar industrial complex is a tall order for the immediate future. But here's the twist. Some companies, like Helion Energy, argue you don't need to go to the Moon at all.
Helion is the one backed by Sam Altman, right? How do they get helium-3 if they aren't mining it?
They breed it. Their approach is fascinating. They use a pulsed fusion system. They start by fusing deuterium with deuterium. That reaction has a 50-50 chance of producing helium-3 as a byproduct. So they run that reaction, capture the helium-3, and then feed it back into the machine to fuse with the deuterium.
So it's a closed loop. They're farming their own fuel.
Exactly. They call it a fuel cycle. By doing this, they sidestep the scarcity issue entirely. But that brings us to the second problem I mentioned, the temperature.
Right. You said DNT needs 150 million degrees. What does helium-3 need?
About 200 million degrees or more. It's significantly harder to push those nuclei together because they have a higher electrical charge. They repel each other more strongly. It's called the Coulomb barrier.
That sounds difficult, but not impossible if we're already hitting 150 million. But what about the other fuel you mentioned? Hydrogen, boron. That sounds oddly mundane. Boron is in laundry detergent, isn't it?
It is borax. It's incredibly abundant, stable, and non-toxic. The reaction is called P-11. A proton, hydrogen, meets a boron-11 atom. This is the true dream of fusion. No radioactive tritium, no scarce helium-3. You literally fuse hydrogen and boron, and the output is 3 alpha particles, basically just helium nuclei.
Clean, abundant, no radioactive waste. Why isn't this the only thing we're researching?
Because the physics is punishing. To ignite hydrogen boron, you need temperatures around 3 billion degrees Celsius. We are talking about conditions that don't even exist in the core of the sun. You need 120 kiloelectron volts of energy, compared to just 15 kiloelectron volts for DT.
3 billion degrees. At that point, aren't you fighting physics itself? I remember reading about something called Bremsstrahlung radiation. It sounded like a showstopper.
You've done your homework. Bremsstrahlung is German for breaking radiation. When you have a plasma that hot, the electrons are whizzing around at relativistic speeds. When they pass near the heavy boron nuclei, they get deflected and emit X-rays. These X-rays carry energy away from the plasma.
So the plasma cools itself down?
Rapidly. In a standard magnetic bottle for P-11, the Bremsstrahlung losses can actually be higher than the energy produced by fusion. You're pouring energy in, and it's leaking out as X-rays faster than you can fuse atoms. For decades, physicists said P-11 was impossible for this exact reason.
But clearly, someone thinks it's possible, or we wouldn't be talking about it. Who is crazy enough to try this?
TAE Technologies, formerly Tri-Alpha Energy, is the big player here. They've been working on this for over 20 years in secret before coming out recently. They use a machine called a Field Reversed Configuration, or FRC. It looks more like a long tube than the donut-shaped tokamaks like ITER.
How does a tube help with the X-ray problem?
Their argument is that they can create a non-thermal plasma. Essentially, they keep the electrons cooler than the ions. If the electrons are cooler, they emit less Bremsstrahlung radiation, but the ions are still hot enough to fuse. They also use massive particle beams to keep the plasma spinning and stable. It's a very different beast from standard fusion.
This seems to be a recurring theme with these exotic fuels. The standard government approach, the tokamak, is designed for the easy fuel. To use the perfect fuel, you have to reinvent the machine entirely.
That's the pivotal insight. The tokamak was designed in the Soviet Union in the 1950s specifically for DT fusion. It is great at trapping heat. But for exotic fuels, trapping heat isn't enough. You need to manage particle flow and magnetic pressure in ways the tokamak struggles with. That's why private companies like Helion and TAE are designing these weird, elongated machines. They are optimizing for the fuel, not just the reaction.
Let's talk about the zero waste claim in the title of this episode. If we get PB11 working, is it truly zero waste, or is that just marketing fluff?
It is mostly true, but physics is messy. The primary reaction, proton plus boron, produces only alpha particles, helium-4, which are safe and useful. However, in any plasma, side reactions happen. You might get a tiny bit of carbon-12 forming, which can release a neutron. But the neutron flux is orders of magnitude lower than DT fusion, like 0.1% of the radiation. You wouldn't need a 10-foot thick concrete containment dome. You could practically run these in a light industrial warehouse.
Which changes the economics completely. If you don't need the massive shielding and you don't need the steam turbine, the power plant shrinks.
It shrinks and it simplifies. Helion, for instance, talks about shipping their generators on trucks. Because they use direct energy conversion, they're basically just solid-state generators. The magnetic fields expand and contract, pushing electrons through a wire. It's almost like a combustion engine piston, but magnetic.
I want to circle back to the skepticism, though, because 3 billion degrees is incomprehensible. Are we close, or is this just venture capital bait?
It is certainly high risk. TAE has a machine called Copernicus, designed to reach reactor-relevant conditions, and they're planning a successor, Da Vinci, to actually put power on the grid. They've proven the stability of their plasma, which was the big unknown, but heating it to 3 billion degrees without losing control is still a massive hurdle.
And Helion?
Helion is arguably ahead in terms of temperature relative to their goal. They hit 100 million degrees recently, but they have to prove they can do it repeatedly, like a piston firing 10 times a second for months on end. Right now, we're seeing pulses. The gap between one cool pulse and commercial power plant is engineering reliability.
It's interesting that the competition isn't just between fusion and solar or wind, but between fusion and fusion. It feels like a VHS versus beta format war, but with the power of the stars.
It really is. And the stakes are different. DT fusion, the ITER path, is a baseload solution. It's designed to replace massive coal or fission plants. But exotic fusion, if it works, could be decentralized. You could have a 50-megawatt hydrogen boron plant powering a data center directly with no radioactive footprint.
And boron is everywhere? We won't be fighting wars over boron mines?
Exactly. We have enough boron in seawater and salt flats to power the Earth for billions of years. It effectively decouples energy from geopolitics.
That is a beautiful thought. But before we get too star-eyed, what is the one thing that could kill these exotic fusion dreams? Is it just the temperature?
It's the energy balance, what we call Q. You have to put energy in to heat the magnets, heat the plasma, and run the cooling systems. With DT fusion, the reaction is so energetic that once it starts, it helps heat itself, alpha heating. With PB11, because of those X-ray losses I mentioned, the margin for error is razor thin. If your machine isn't perfectly efficient at capturing that energy back, the math just doesn't work. You end up with a very expensive space heater.
So efficiency is the bottleneck. It's not just about making the fire, it's about catching the heat.
Right. That's why direct conversion is so critical. A steam turbine is maybe 35–40% efficient. Direct conversion can theoretically be 70% or higher. For exotic fuels, that high efficiency isn't a bonus. It's a requirement to overcome the physics difficulties.
It really does feel like we are on the precipice of a shift in how we think about nuclear energy. For decades, nuclear meant danger, waste, and massive government oversight. Exotic fusion paints a picture of nuclear that is benign.
Benign and limitless. If DT fusion is the brute force conquest of the atom, exotic fusion is the finesse approach. It's judo. It uses the particle's own charge to do the work. It's harder to learn, but much more effective once you master it.
So, if you had to bet, Alex, 20 years from now, are we running our toasters on helium-3 from the moon or hydrogen boron from the laundry aisle?
I'd bet on the terrestrial solutions first. Whether it's Helion breeding their own helium-3 or Tay cracking the code on boron, I think the logistics of space mining are a hurdle we don't need to jump yet. If hydrogen boron works, it wins. The fuel is free, and the waste is non-existent. It's the end game for energy.
The end game. A world where energy as cheap and clean as information. That's a future worth sweating the engineering details for.
Picture the scene. It's the height of the Cold War. You have generals sitting in a smoke-filled room staring at a whiteboard. They have nukes, they have jets, they have submarines. But one of them slams his fist on the table and says, "Gentlemen, what I really want is to shoot a donut made of lightning at a Soviet tank."
And for once, Theodore, you aren't actually exaggerating. That is a surprisingly accurate summary of the Air Force's interest in what they called self-stabilizing plasma structures.
I try to keep my absurdity historically accurate. But we're digging into a very specific, very weird corner of military history today, the Nachamkin report.
Right. We are unpacking the work of Jack Nachamkin and the broader obsession with directed energy warfare. This isn't just about lasers. Lasers are easy. You point light, it hits thing gets hot. This was about trying to create a projectile made of pure plasma that wouldn't just dissipate the second it left the gun.
Which is physically impossible, right? I mean, plasma is just superheated gas. It wants to expand. It wants to cool down. Trying to shoot a ball of plasma is like trying to shoot a snowball through a sauna. It should melt instantly.
Under normal circumstances, yes, and that is exactly why the Air Force was funding research into what are technically called force-free time-harmonic plasmoids. That is the specific concept Jack Nachamkin was modeling. The goal was to find a mathematical loophole in physics where a ball of plasma could hold itself together using its own magnetic fields.
Force-free time-harmonic plasmoids. Say that 5 times fast. It sounds like something Doc Brown would invent after hitting his head on a toilet.
It's dense physics, but the logic is fascinating. The force-free part refers to a state where the magnetic pressure inside the plasma perfectly balances the plasma pressure trying to push out. Essentially, the magnetic field lines wrap around the plasma in such a complex, twisted way, usually a toroid or donut shape, that they act like a straitjacket.
So it's a self-containing magnetic prism. A ghost trap, but for lightning.
Exactly. If you could pull it off, you wouldn't need a physical canister to hold the energy. The energy is the canister. Nachamkin's work, particularly his papers from the early 90s, was looking at the math to see if these structures could exist in a stable state. He was solving Maxwell's equations to prove you could have a standing wave of electromagnetic energy that didn't just fly apart.
But why? I mean, aside from the obvious, it looks cool factor, why was the military so desperate to make ball lightning a reality? Because that's what we're talking about here, weaponized ball lightning.
Ball lightning is the perfect description. In fact, if you look at military journals from the 1960s, like the article Ball Lightning as New Weapon, published in 1963, they were already obsessed with this. The appeal was range and damage. A laser moves at the speed of light, but it can be blocked by smoke, mirrors, or rain. It loses power over distance due to atmospheric scattering.
But a plasma donut?
A self-stabilizing plasmoid would act like a physical bullet. It has mass. It carries an immense electrical charge. If you could fire one of these things into the intake of a MiG fighter or slam it into a radar dish, it wouldn't just burn a hole. It would discharge massive voltage, frying every electronic circuit instantly. It's an EMP grenade that you can aim.
The ultimate taser. But this goes back to the Cold War paranoia you mentioned. The US wasn't just researching this because they had extra budget. They were terrified the Soviets were already doing it.
That was the driving force behind so much of this. There were reports, mostly unverified, of Soviet scientists like Pyotr Kapitsa working on ball lightning theories. The CIA even had declassified documents from 1967 where they considered weaponizing lightning by using ionized wires to guide bolts from storms. The leap from guiding natural lightning to creating artificial ball lightning was the logical next step in that arms race.
It feels like we were trying to reverse engineer a UFO. You hear stories about Foo Fighters in World War II, glowing balls of light following planes. Then 50 years later, the Air Force is paying guys like Nachamkin to prove that those glowing balls could be mathematically real.
That is a huge part of the cultural legacy here. A lot of the research into plasmoids overlaps with the study of unidentified aerial phenomena. If a pilot sees a glowing orb moving at Mach 4, the Air Force has two questions. Is it aliens? Or did the Russians figure out how to stabilize a high-energy plasma toroid before we did?
So Nachamkin sits down, does the math, and says, yes, theoretically, a plasmoid donut can exist without exploding. Why aren't we seeing these on the battlefield today? Why isn't there a plasmoid cannon mounted on every destroyer?
Atmosphere. The atmosphere is a bully. Nachamkin's math often works beautifully in a vacuum or under very specific conditions. But the second you fire that plasmoid into dirty, thick air, things get messy. The air resistance strips energy away. The stability is incredibly fragile. You might be able to generate a force-free plasmoid in a lab for a nanosecond, but keeping it stable while it travels a mile downrange, that is an engineering nightmare.
The energy requirements must be insane, too. You have to generate enough magnetic force to counteract the pressure of superheated gas.
Colossal. You're talking about power levels that usually require a building-sized reactor, and you're trying to shrink it down to something you can put on a plane or a tank. However, the research wasn't a total failure. It pivoted. Instead of shooting plasma bullets, the Air Force moved toward high-power microwaves, or HPMs.
Explain the difference, because microwave weapons exist, right? We have things like Thor now.
Right. Thor, the tactical high-power operational responder, is a real system used for drone defense. Instead of trying to keep the plasma together in a ball, they just use the directed energy itself. They blast a cone of microwave energy to fry electronics. They realized they didn't need the bullet shape to get the kill. They just needed the energy transfer.
So the self-stabilizing plasma was a stepping stone. They wanted a cannonball, realized making a cannonball out of lightning is really hard, and settled for a death ray instead.
In a way, but the dream of the plasmoid hasn't died. It actually migrated to fusion research. The same physics Nachamkin was looking at, keeping plasma stable using its own magnetic fields, is critical for fusion energy. If you can make a miniature self-sustaining plasma ball, you don't just have a weapon, you have a miniature sun that produces clean energy.
Which is the classic military-industrial irony. We tried to build a gun, failed, and accidentally helped figure out how to power the world.
Or at least, we ruled out one way of not powering the world. And let's not forget, the Directed Energy Directorate at Kirtland Air Force Base is still very active. They are still funding research into atmospheric propagation of plasma. The Nachamkin report and that era of research proved that while the force-free state is mathematically possible, achieving it essentially requires you to trick the laws of thermodynamics.
Tricking thermodynamics is my favorite pastime. But there is also this weird fringe element to it. You look up Nachamkin or plasma structures online now, and you fall into a rabbit hole of conspiracy theories. People think this research led to secret anti-gravity drives.
Because the physics looks like magic. When you describe a self-contained glowing orb that defies gravity and moves independently, that sounds like a UFO. But in the report, it's just vector calculus. The anti-gravity part is usually a misunderstanding of how magnetic fields interact. A strong enough magnetic field can levitate things. We do it with frogs in labs. But that doesn't mean the Air Force built a flying saucer.
They just built a really expensive math problem.
A math problem that helped define the limits of directed energy. We know now that if you want to disable a missile, a laser or a microwave burst is more efficient than a plasma ball. But the concept of the force-free plasmoid remains the holy grail of plasma physics. If you solve it, you solve fusion.
And if you solve it, you can finally shoot a donut of lightning at a tank, which, let's be honest, is still the coolest possible outcome.
I'm sure the generals in that smoke-filled room would agree with you. Picture this. You are a Top Gun pilot. You're cruising at 30,000 feet, you've got millions of dollars of sensors strapped to your chest, and you see something that shouldn't exist. It's not a plane, it's not a drone,
it's a glowing orb. Maybe it's a sphere with a cube inside it. Maybe it's a ball of fire that chases you, matches your speed, and then vanishes without a sonic boom. Your brain goes to the movies. You think aliens. You think non-human intelligence. Because the thing is moving like it has a mind of its own. It stabilizes itself against hurricane force winds. It reacts when you lock your radar on it. But what if I told you that the behavior you're seeing, that erratic, lifelike, impossible movement, isn't evidence of a pilot inside the craft? What if it's evidence that there's no craft at all? Today, we are walking right into the middle of a scientific crossfire. On one side, we have the UAP phenomenon, unidentified aerial phenomena. On the other, we have the quiet, terrifying world of directed energy research. We're going to ask a question that might upset both the UFO believers and the debunkers. Are these glowing orbs extraterrestrial technology, or are they high-energy plasma structures, ghosts made of ionized air projected by lasers?
Part 1. The Foo Fighters and the Valley of Light. Before we get to the high-tech lasers, we have to look at the history, because pilots have been seeing these things long before we had the technology to fake them. Go back to World War II. It's 1944. You have Allied pilots flying night missions over Germany. They start reporting these balls of light following their formations. They called them Foo Fighters. The pilots were terrified. They thought these were secret Nazi weapons. The funny thing is, after the war, we checked the German records. The German pilots had reported the exact same thing. They thought the fireballs were American weapons. Nobody was shooting at them. The orbs would just dance off the wingtips, glow red or orange, and then zip away at impossible speeds. It was the first modern instance of the intelligent orb mystery. Fast forward to the 1980s, to a tiny valley in Norway called Hestalen. This place is basically the mecca of orb phenomena. For decades, people in Hestalen have seen lights, white, yellow, red, floating in the valley. They hover for hours. Sometimes they streak across the sky. And this isn't just folklore. Scientists have set up permanent monitoring stations there. What they found in Hestalen is crucial for our puzzle. They used spectral analysis, basically looking at the chemical fingerprint of the light, and found that these orbs weren't just light, they were burning. They contained scandium, titanium, and other elements found in the valley's soil. One leading theory, developed by researchers like Jader Minari, is that the valley itself acts like a giant natural battery. You've got copper on one side of the river, zinc on the other, and acidic water in between. Under the right atmospheric conditions, the ground discharges electricity into the air, creating a free-floating ball of plasma. Now here's the kicker. These natural plasmas in Hestalen, they show up on radar. They have a physical signature. And sometimes, when you shine a laser at them, they react, they pulse, they change their flash rate. It looks like intelligence, like it's communicating, but it's likely just physics, a plasma structure reacting to an influx of energy. So keep that in your pocket. We have a precedent for glowing, radar-reflective orbs that act weirdly alive but are 100% natural. Now, let's see what happens when the military decides they want to build their own.
Part 2. Project Condign and the Plasma Smoking Gun. If you think the government has been totally silent on this, you haven't read the British Ministry of Defence's Project Condign report. This is a massive, secret study on UAPs completed in 2000 and declassified a few years later. It is a fascinating read because the author, who remains anonymous, basically admits that UAPs are real. But, and it's a huge but, the report concludes that they aren't spaceships. The report states, quote, that UAPs exist is indisputable. They clearly can exhibit aerodynamic characteristics which are well beyond those of any known aircraft or missile, either manned or unmanned. So what are they? The Condign report bets the house on something called buoyant plasma formation. The theory is that under certain conditions, maybe meteorites entering the atmosphere, maybe magnetic anomalies, charged plasmas form. These plasmas are buoyant, meaning they float. They are electrically charged, so they have a magnetic field. And here's where it gets wild. The report suggests that the magnetic fields from these plasmas might be so strong that if you get too close, they scramble your brain.
They explicitly mention that close encounters could cause hallucinations due to the electromagnetic influence on the temporal lobe of the human brain. So you see a ball of light, your brain gets zapped by a magnetic field, and suddenly you're remembering an abduction scenario. But the most chilling part of Project Condign wasn't the natural explanation, it was the recommendation. The report basically said to the UK military, hey, these plasma balls are real. They confuse radar, and they move impossibly fast. We should figure out how to weaponize this. They realized that if you could artificially create a plasma orb, you would have the ultimate camouflage. You could create a ghost target that an enemy missile would lock onto while your real plane flies away safely. And that leads us directly to the US Navy.
Part 3. Weaponizing the ghost. Let's talk about a patent, specifically U.S. Patent 10197442. It was granted in 2019 to the U.S. Navy, and the inventor is listed as Alexandru Henning. The title is a mouthful, but the concept is straight out of science fiction. It describes a method for creating laser-induced plasma filaments. Here's how it works simply. You know how lightning is just electricity turning air into plasma? Well, if you fire an ultra-short, ultra-intense laser pulse, you can rip the electrons right off the air molecules at a specific point in space. You are literally ionizing the air with light. This creates a glowing spot of plasma. Now, if you have a system that can fire these pulses thousands of times a second and move the focal point around, you can draw a 3D shape in mid-air. It's like a hologram, but it's not a trick of the light. It's physical. It emits heat. It emits infrared light. It reflects radar. The patent explicitly talks about using this to create phantom images to fool heat-seeking missiles. Imagine you're a fighter jet. A missile is locked onto your heat signature. Instead of dropping a flare, you use a laser to project a ball of super hot plasma 100 yards away from your plane. The missile sees this hotter, brighter target and goes for the ghost. Your plane vanishes into the dark. This isn't just theory. We know the Pentagon has a program called Nemesis, netted emulation of multiple element signature against integrated sensors. That is a fancy way of saying we are going to flood the enemy's radar screens with fleets of ships and planes that aren't there. We're talking about creating entire phantom battles.
Now, think about the famous Tic Tac UFO sighting by the USS Nimitz carrier group in 2004. Commander Fravor described a white object, roughly the size of a fighter jet, with no wings, no exhaust, moving erratically. It mirrored his movements. When he tried to cut it off, it accelerated instantly. A laser-induced plasma decoy has no mass. It has no inertia. If I shine a laser pointer at the wall and flick my wrist, the dot moves across the wall at thousands of miles an hour. It can stop instantly. It can change direction instantly. Because the dot isn't an object, it's a projection. If the Tic Tac was a plasma filament being projected from a satellite or a submarine or another aircraft, it could do everything Fravor saw. It would glow. It would appear solid on radar because plasma reflects radio waves, and it would break the laws of physics because it doesn't have to obey them. Even that weird detail pilots report, the cube inside a sphere, Ryan Graves, a Navy pilot, said they saw these things every day off the East Coast. A dark cube inside a clear sphere. Well, if you need a radar reflector to stay aloft, you might put a physical reflector, a cube, inside a balloon or a plasma shield. Or the plasma itself forms a spherical sheath around a central point. It fits the description disturbingly well. Part 4, the uncanny valley of tech.
So, case closed. It's all secret Navy tech? Well, not so fast. Because there are things about the behavior of these orbs that make the projection theory tricky. First, the duration. Maintaining a plasma filament takes a tremendous amount of energy. The Navy patent talks about short bursts for decoys. The Hessdalen lights, however, hover for hours. If the Tic Tac was a projection, the power source required to keep that plasma stable and glowing for that long while moving it around would be massive. Where is the projector? And then there's the intelligence. Pilots describe the orbs as acting playful or aggressive. They seem to anticipate maneuvers. If it's a decoy, that means there's an incredibly sophisticated AI or human operator somewhere controlling that dot with zero latency. But there's another angle.
a weirder one: dusty plasmas. Some physicists have proposed that under certain conditions, plasma can organize itself into structures that mimic life. In lab settings, plasma crystals can form, grow, and even replicate. In 2007, a team famously published research suggesting that plasma particles could form a double helix, like DNA. If you look at how ball lightning behaves, it enters houses, floats down hallways, avoids obstacles. It looks alive, but it's likely following electromagnetic field lines, drafts, and electrostatic gradients. It's self-stabilizing, not because it has a brain, but because it's a stable system seeking equilibrium, like a bubble. When a pilot locks a radar onto a plasma orb, they are hitting it with electromagnetic energy. If the orb is a natural electrical phenomenon, it might physically react to that energy boost. It might expand, brighten, or shoot away. To the pilot, that looks like evasive action. To a physicist, it looks like a reaction.
So we are left with a spectrum of weirdness. On one end, you have rare natural atmospheric events, Earth lights, ball lightning, that we barely understand. On the other end, you have cutting-edge military deception technology, Project Nemesis, plasma decoys that are designed to mimic real aircraft. And somewhere in the middle, you have the pilots. They are seeing something that glows, moves instantly, and ignores gravity. If it is military tech, it means the US or China or Russia has mastered directed energy to a point where they can project physical hallucinations into the sky. Think about the implications of that. If you can create a fake fleet of bombers on an enemy's radar, you can win a war without firing a shot. Or you can start a war by making it look like the enemy fired first. The overlap between UAP studies and directed energy research is the most fertile ground for answers right now. The military knows plasma is the perfect decoy. Nature shows us plasma can be stable and weird. The orbs aren't necessarily little green men. They might be little balls of lightning, or they might be the 21st century version of a magic lantern show. Next time you look up and see a light moving in a way that makes no sense, ask yourself, is it a visitor? Is it the Earth burping up electricity? Or is it a trick of the light, designed to make you blink?